Torque is a spinning force. In the instance of this wheel spinning on the ground, the torque applied to the wheel axle creates a linear force at the edge of the tire where it contacts the ground. If we look at the equation then, torque equals force times distance, and it can be measured in inch-pounds or Newton-meters. As an example, torque equals 1 Newton, the force, times 0.5 meters, the distance, giving us an answer of 0.5 Newton-meters. Let's go into force effect motion and have a look at what we can do here with mechanisms and measure torque. I'm going to start out in force effect motion. Here's an example of windshield wiper. And I've put a trace at the end of point B at the end of the windshield wiper, and I can follow its path. Let's look at another example. In this case, we're going to look at 4 well-known mechanisms: 4-bar, crank slider, Watt, and Stephenson. The Watt mechanism is named after James Watt, a famous Scottish inventor and engineer. And today, when we talk about units of power, we talk about kilowatts. I'm now going to create a new diagram and have force effect motion mimic the arm of my robot. First thing I'm going to do is check the units. I want to do this in metric, and my length units of meters is correct. We'll start by placing the first element and then changing the length of that element to 0.25 meters. Next thing I'm going to do is place an actuator. This is the equivalent of the VEX motor. And with that actuator placed, I can start the animation, and you can see it's going 1 full revolution, 360 degrees. I want to change that, so I select the actuator and change the angle to 90 degrees. Start the animation again, and this time it goes through horizontal to vertical. You can change a number of values in here, and one that may be of interest is the actuator speed. It's measured in revolutions per second, so you can compare that to the revolutions per minute that's normally listed for the motor. Next thing I can do is put a trace point at point A, start my animation again, and we can see the path generated by point A. Being a fixed length is a radius, therefore it's a quarter circle in this case. Selecting one of the elements gives me a velocity of 1.571 meters per second. I'm now going to open this up in force effect. So in force effect, the diagram has been brought in. I'm just double checking my force units, which I want to change to newtons. Up in the top right hand corner, there's some important information about the degrees of freedom. At the moment, it's indeterminate. I want to change it to an equilibrium state. To do that, I'm going to select B and change it to grounded, and you can see it is now in equilibrium. Add a force of 1 Newton, and now I can see the torque is 0.25 Newton meters. That's 1 times the length, 0.25 meters. I can review the results in the report, and I can email that to myself or other members of the design team. Let's change some values and see the effect. I'm going to change that from 0.25 meters to 0.125. So again, thinking of our equation, it's 1 times 0.125, giving us the torque of 0.125 Newton meters. Changing it again, in this case 0.5, and by now you should have that. It's 1 times 0.5, giving us 0.5 Newton meters for the torque. I'm going to back out to my gallery, which saves the data. I could send that diagram by email to myself or to my Autodesk 360 account. Let's start a new diagram. In our robot, we normally have an arm that swivels, so I'm going to create that situation in force effect. I'm going to start by creating a vertical element of 0.4 meters. I'm going to put a support in at point A, and that's going to be grounded. Next thing I'm going to do is put in another element, and this will represent a 0.25 meter long arm. Now in this particular case, the arm will pivot, and I want it to be set at 330 degrees initially. Now even though it will pivot, what I want to do is I want to fix that particular point so I can do my calculations. So I've made it a welded joint. Now add the load of 1 Newton. With my value input, I can now see that the torque is 0.125 Newton meters. So how do we calculate that number? Well, we know the load is 1 Newton, but the key thing here is the distance. That's from point C to that vertical line AB. That's the distance to the pivot point. Let's change some of those values. I'm going to change that angle from 330 to 315 degrees. So that's effectively a 45-degree angle between the vertical element and the arm. Deleted that construction line. I'm going to put it in again. And of course, this time we see that the distance is 0.177 meters. And that makes sense because we can see the torque is 0.177 Newton meters. Let's change the value so that the arm is horizontal again. Delete that construction element. And again, we're back to what we had in the previous example. 1 Newton times 0.25 meters.